No more question, right?
I have one basic question.
Okay.
If you go to your untitled file,
This?
Jupyter Notebook.
Jupyter Notebook?
Yeah.
Okay.
For the other one. Oh, the untitled one.
This?
Yeah. So when you use linear space or a range, it gives you a range between certain numbers, but it excludes the last one. But when you use linear space, it includes the last one as well.
Yes. Look at 12 and 4 is that. So that is the main difference between bin space and a range.
Okay. Because a range, when we use it, does not include the last number.
Can we do that? You cannot actually do 12 to 4. I think you can do 4 to 12, but you cannot do backward for a range. But for linear space, you can. Let's take a look at the code briefly, and then you go through the tutorial in homework. How about that? Or you do homework for understand it fully. Then we can move on for ODE. Okay. Let me show something that is not inside the presentation file. SymPy. Oh, okay, by the way, quickly look at this. Second order accuracy, I show it to you somehow, and you will do this in homework, that when the gap reduced by 10 times, the error reduced by 100 times. And I show it to you numerically. So, fourth order, 10,000 times. But you go through that by yourself in your homework, okay? Let's talk about SymPy. How do you integrate it analytically? Any idea? Okay, SymPy, for the analytical result from SymPy, does it work every time? No. What about numerical method? Does it work every time? Pretty much. Yeah. As long as your function has a value, it works. But SymPy works for certain case. Okay. Analytical solution doesn't exist for every cases. That's why we have to use this. Okay. So notebook, you go through it by yourself. Let's talk about SymPy integration, okay? Look at this line. sm.integrate. Sm, let me go back to the top. Sm is SymPy. Import SymPy as Sm. So that is SymPy. And we do double integration. So I have, for example, function 1, function 2, function 3. Function 1, the limit is just constant, and the function is just number 1. Nothing, just number 1. So I do sm.integrate, parenthesis, 1, comma, this tuples, comma, and another tuples. So the first one, I press Shift Tab. It shows me the signature, those arguments. So integrate f and then variable, right? So function is f is 1. That's a function. And variable, the first one is inner limit. So the variable is x, and we integrate from 12 to 16. And outer limit is, the variable is y, and when we integrate from 1 to 3. And we send it as a tuple. Okay? So when we do this, it do double integration. What if the function inside is not number 1? So I type it, xs squared plus 7y. The rest is the same, it do the integration. What if the limit of integration is not a constant? It's not 16, but it's y. How do I do it? I just put y with that. Done. Pretty easy, right? Good. Everything is the same. So this is a function, and first tuple tell me the limit of integration for the inner integration. This one is outer integration, and the limit. I take xs as a variable, it integrates from 12 to y. Of course, xs and ys, you have to do this line first. You have to declare it as a symbol, sm.symbol fy. Okay. If you want to do double integration, just that. It gives you the value. Or you want to do single integration twice, you can. Look at this. I integrated from x from 12 to ys, I get the expression, and from that expression, I integrate from 1 to 3, where y is unknown. I get the answer, and they are the same. Okay? And my result from double SimPy is the same as the one that I get from analytical solution. Okay? And it is the same as what? Double quad, DBL quad. That's the automatic function that you use. Okay? DBL quad. So you can do DBL quad and integrate directly. To know what's that, press Shift tab. You get the signature function A, B, G func, H func. That's a limit of integration for the inner one. Good?
Excuse me, sir.
Yes.
Is there any special reason why you use SX instead of just X?
To show you that it doesn't need to be the same. The one over here in the quotation mark is for the display. You see this part? That is for the display. But the way that you interact with it in the code, you have to use this part. Okay. So when you interact with it in the code, you use that.
Yeah,
but that is for the display.
Yeah, if we say x comma y is equal to central symbols, that's fine too, right?
Work too, yeah, it worked too. But I use x as so that I know that that is x for SimPy as well. So, okay, no more question, right? I have question. Okay, who want to answer? Or you want to go back from me? This is George. Okay, George. If I have, you see this integration limit y. You see that y?
Yes.
So, what should be that y value? Instead of y, I want to put a constant. Oh, let's not do that. Instead of 3, you see that number 3? Integrate from 1 to 3. Instead of 3, I want to put something else. What should be that something else so that the whole integration will be equal to 20?
Like change the 3 just to...
Change 3 to what? I mean, you don't know the answer, I don't know either, but what is the method to solve for that? So instead of number 3, you see this is double integration, right? I integrate from 12 to y and 1 to 3, and the answer is something like that. Oh no, that's not the answer. Oh, the answer is minus something. The answer is minus 1,400. If I want the answer to be just minus 1,000, instead of number 3, I should use what? Conceptually, how do we solve for this kind of question, George?
Probably have back substitutions.
Naturally, what is the method for solve for one unknown, one function, one unknown?
One function.
Is this one function, one unknown?
Yeah.
Instead of 3, it should be something else. And if that something else is correct, I should get minus 1,000 instead of minus 1,400. Is this one function, one unknown? Yeah.
Yes.
What is the method for that?
Probably you f-solve.
F-solve, of course, that works. That's a sci-fi function. So what about the name algorithm that you can use without anything from sci-fi? Just a name.
No idea.
Good find.
F-solve use several kind of numerical method. One of them that can use for this is what? Fixed point. Nah, there is a better method. Yes, fixed point. Bisection, yeah. What else?
The Newton
You can use Newton-Raphson, right? So if I ask you instead of 3, what should it be so that the whole integration result equal to minus 1000? You use Newton-Raphson. So the function is that thing minus 1000. If the guess is correct, you get 0. If the guess is not correct, you get some number. And you use Newton method to adjust until that equal to 0. Good?
How do you use for solving an integration?
You have to think about the whole thing as fx, where x is the integration limit.
Okay, right.
And then fx minus 1000, that is your function to solve by Newton method. Yes.
So can I put like a constant a on that equation and I use simplify to solve? So
It should. Simplify should also do the job. I don't know exactly, I didn't try, but Simplify should also. As long as Simplify can do the whole integration,
yeah.
just find that thing, Simplify will too. Okay. More, do you have more, no more questions?
Also, we evaluate the inner integral first.
Yeah.
Then we put fxy equal to 1000 to solve for. Then we can make it equal to a or b. Then
You have to look at the whole as a function of something equal to 0. And that something is that number 3. So instead of number 3, we put that as z.
but you
So
say you want us to make it equal to 1000.
I mean, your function will be, or by the way, you know how to write the LaTeX code in here, right? Do you? Oh, it's not big enough. At the end, you want to solve for z. What is the right z that make fz equal to 0? So if you don't put the right z, you put z equal to 3, you get minus 1400, right? So minus 1400 minus 1000 doesn't give you 0. But if that z is the correct one, then this will be 0. So it is one function, one unknown. What is that function? That function will be just this line. The answer from this is what? One number, right? Just one number. So if you change from, if you have to change something about that, okay? What if this have to do with, that is with Newton method, right? What if it's like coupled with Newton Jacobian, can you solve it? System of nonlinear equation that contain integration. Can you solve it? Probably yes. It's kind of black box, but you have several of them. So let's say instead of first equation, oh wait, what's that? So you have 3 double integration and 3 unknown, and it equal to 0 simultaneously. You solve that by using Newton Jacobian. Easy, right? The code, I already made it for you. Is it easy? Yeah, you have to try. But theoretically it works, right? Okay. Let's do ODE. Oh, you want more question from me? No, not yet. Okay. ODE. I don't think we can. Okay, we have 23 minutes. We can cover a little bit. For ODE, the whole thing is quite a lot. We don't cover any derivation, but just to let you know, the derivation most of the time come from Taylor series expansion. There are several tricks in Taylor series expansion with lengthy map. Then they get the result. So we skip the whole derivation and show you just what is inside and how do we do it. Okay? There are two kinds of methods: constant step, okay, and automatic step or adaptive step. Adaptive step is domain prints 5.4. Domain prints 5.4 is the standard that used in MATLAB. Okay, it's quick and it's better than RK45. So I changed from RK45 to domain prints 5.4. The rest is a constant step. Okay, that is to categorize it into adaptive or constant step. Another way to group them is implicit or explicit. Implicit method is more stable than explicit method. Okay, more stable means you can use a bigger jump. Or first of all, I forget. ODE is to solve this kind of thing. dy by dx equal to some function. Okay, if you have dy by dx equal to some function of x and y, and you want to solve for not just one value but every point in y, whole function. So let's say your function look like exponential function. So we have dy by dx equal to y, and we want to solve for it. The answer is not just one point, it's the whole line or several points. Okay, we cannot get the answer as a function, but you can get the whole line. You can get several points. Okay, let's come back to this. dy by dx equal to y. We want to solve that. We need some kind of initial condition or boundary condition, right? So for x equal to 0 to x equal to 10, that is where this equation is valid. And we want to solve for y between x equal to 0 and x equal to 10. We know that at x equal to 10, y equal to 1. Okay. Analytically, you move this to the denominator, integrate both sides, substitute the constant, and find it. I get y equal to e to the power of minus 10 times e to the power of x. That's analytical solution. Analytical solution gives me the answer as a function or a line, the whole line, right? Numerical answer gives me several dots. Okay. And let's skip SimPy for the time being. First one we have explicit order. We will go to SimPy later. Explicit order, I use the slope at the current point to find the next point. That is explicit order. So basically I have dy by dx equal to function of x and y. So dy by dx is slope, right? I use slope at the current point to get the next point. So dy by dx equal to fx, so that is slope. Next point is current point multiplied by delta x or h multiplied by the slope. So that will be the way I get the next y value. Okay. In a graphical format, you have the slope at the current point. You are at that point, you have the slope, you do linear extrapolation, then you get the next point. That equation that you just have seen is the linear extrapolation from the current point. Okay, that is explicit order. It's not stable, it's explicit method. And it's very easy, right? It's similar to our interpolation or extrapolation, right? Linear extrapolation. So we use slope. Slope is divided by dx multiplied by delta x, we get delta y. Delta y plus the current y is the next y, just that. That is explicit Euler method. It's not stable. How about implicit Euler method? For implicit Euler method, we use slope at the next point to get the value at the next point. But if we don't know the next point, how do we get the slope at the next point? Look at the formula. It looks the same. This part is the same. This part is the same. This part is very similar, except the slope, it is defined at next point. Xn plus 1 and yn plus 1, right? But we don't know yn plus 1 until we solve this thing. So yn plus 1 is a function of yn plus 1. It's one function, one unknown. You use, of course, you use f-solve, but the name of the method, Newton-Raphson. So you move this to this side, you get g of yn plus 1 equal to some expression, and then you solve for it. The right yn plus 1 make gy plus 1 equal to 0. So we use the slope at the next point to find the next point. But we don't know the next point yet. But we have one equation, one unknown. We use Newton-Raphson to solve it. Okay. In the graphical form, it looks like this. First, you are at this point, okay, and your step, which is your jump. Let's say your edge is that big. You use that slope at this point, and then you extrapolate based on that slope. Okay. But this time we solve from x equal to 10 to x equal to 1. We solve backward. How do I do anything like that? So let's say at x equal to 10, we get the point value, but we want to move back to x equal to 1. So I use the slope at the next point. The next point may be this point. The slope at that point is just that much. So I use that thing over here, extrapolate, and get the next point. So we use the slope at the next location to find the next location. But when we actually doing it, it's not this easy because we don't know the next location yet. So we have one function but unknown, then we solve for it. Okay? Yes?
I see that there are two unknowns actually, because you don't know the slope as well as you don't know the point.
Do you know the expression f? Mm-hmm. Expression f is the right hand side. You know the expression. It may be x plus y plus something, or some strange function, but you know the expression, right? And it requires the value of x and the value of y. If you put x and y in, then you can calculate right hand side. Okay. X at the next point, we know. We specify it. Y at the next point, we don't know. But what I promise you here is, if we get x at the next point, and we put some number in, we can calculate this part. Okay? So let's say fxy is x squared plus y squared. So you put x in, you square it, you put initial guess of your y, you square it, add them together, that is the slope at the next point. Okay. When you use the slope at the next point, then this part may not be 0 yet, because the next point that you think it is not the right value. Many people just use fixed point iteration, but we can do better, right? You can use, it's a one equation but unknown. Just use Newton-Raphson to solve it. Good?
Yeah.
implicit order is good. Okay, and conditionally stable. It's stable every time. Unstable comes when you try to jump too far. Let's say you use explicit order. You have to jump just a little bit. If you jump too far, you get something like that. The point jump around the solution, it doesn't convert. But explicit method can jump very far. Okay? But implicit method can jump very far. When we say implicit and explicit, it doesn't mean one thing is more accurate than another. Okay? Let me show you some calculation result. The big green is implicit order. The big blue dot is explicit order. Both of them are wrong. Equally wrong. It's a first order method, similar order of magnitude of the error, but one is stable, another one is not stable. Okay. Stability thing, we don't really cover it, but I want you to know just the name. Okay. So for linear stability, we can pick one function, linear function dy by dx equal to y k multiplied by y. So this is like stability analysis. And we have next point equal to current point plus delta x multiplied by slope at the next point. Okay. Slope at the next point is k and yn plus 1. Right? Rearrange it, you get this form. After we rearrange it, you can put next y equal to some function multiplied by the current y. You arrange it in this form already, right? So if we have, instead of yn plus 1 as a function of yn, from some analogy you can say yn is this phi function raised to the power of n multiplied by y0. So we select a test function, okay, to do some kind of analysis to give you the name. What is A stability, L stability? Do we know everything about it? No, but you will know which method is better than which method. Okay. So once we arrange it in this form, you can say that, you can see if we multiply by phi several times, phi to the power of n multiplied by y0, that gives me yn, right? So for it to be stable, yn should not go approach infinity. Should it? No. So they said it's not quite stable if yn go approach infinity. So this means if this thing equal to 3 to the power of infinity approach infinity, then this thing go to infinity, right? It's not stable. For it to stable, this thing has to be like 0.5. 0.5 power infinity is like 0. Okay? So if this phi function is 1 over 1 minus z, and that hk is z. So for z less than 0, if z less than 0, what do we have? So let's say z equal to 2. Phi will be minus 1. Z equal to, for z less than 0, then absolute value of phi will be less than 1. So let's say z equal to minus 99. 1 minus 99 is 1 over 100 is 0.01, so it's less than 1. So for any case where the left half of the real space is stable everywhere, for every cases that z less than 0 is stable, then they call it A stable. Okay. It's just a name from some analysis, but it is also important for you to know that A stable means it's stable. The implicit Euler method is not just A stable, but if you look at this, okay, phi function, they call it stability function, this stability function. So as z approach infinity, phi z approach 0. So this is even better. It is, they call this method is L stable. The fact is, you don't really know what is L stable, A stable, but if it's not stable at all, you can tell. Okay. So when you go to the literature, they say, okay, implicit Euler is both A stable and L stable. It means very, very stable. If it is just A stable, it's okay. If it's L stable, this means it's more stable than A stable. So this is just introduction for you for the name, for you to read further. We don't use it in the test, but we explain you a little bit for implicit and explicit method. Okay?
Excuse me, sir.
Yes.
Is there any consideration for z equal to 0? If z is equal to 0, I mean, how do we characterize the function?
Z equal to 0. Z equal to 0 is 1 over 1 is 1. So the condition for A stability is that for the left half of the complex plane is stable everywhere. For the stability function, I understand that this is not that clear, and it is not to be clear either. But what you want to know is A stable is less stable than L stable, and explicit method is not stable at all. Okay, explicit method is not stable at all. Not stable at all means it do something like that. Okay. Let's move on to how do we use it. Okay. So the way to use it, we have to specify the step. For implicit and explicit method, we have to specify h, right? Order the x, the step. Once we specify the step, for explicit method, you can evaluate the function right away because you use the slope at the current point to get the next point. Right? For implicit method, just need to solve this for the next point. So we need to specify the step first. That is the first thing we need to do. H, how much should be the H? Okay, 4 more minutes. What shall we do? Okay. A better method, Runge-Kutta method. Runge-Kutta method is explicit method. Okay, but it's fourth order accuracy. It's better. 10 to the power 4 times better than implicit method. So the way we use it is, we get the next point based on the linear combination of the slope of the intermediate slope. We use K1, which is the current at the current point, K2, which is the slope at the middle point, K3, the slope at the middle point again, and K4, the slope at the last point. We do weighted average, and then we get the next point. How to get that formula? Why do we have to divide it by 6 or something? They do Taylor series expansion, do some math, and then it becomes like that. So this means it is an explicit method. Look at K1. K1 is the slope at the current point, right? We don't need to do anything, we just substitute the value, we get it. K2 is the slope at the middle point, but we estimate the middle point based on that. That is linear extrapolation. So linear extrapolation uses the slope of the current point, K1. And then we do linear extrapolation again, but this time we use K2. And at the end, we want the final point, we do linear extrapolation based on K3. With this linear extrapolation, weighted average, then you can get the next one. It is an explicit method. It doesn't require Newton method to solve. Just solve it, it's done. Okay. There is another method that is even better than this. But first we have to know about this butcher tableau first. We'll cover it next time, but for now, let's take a quick look at the code. Okay, just one of them. Oh, okay. Do you still remember how to do the plot? Yes? Okay. Implicit method. We have this, right? One equation by unknown. When you solve it, you just use fsolve, like what he said, and it's done. So it's not that difficult. If you have to use fsolve several times, put it in the for loop, and it's done. Okay. Next time is going to be exam in that room. Okay. You will come before the exam time a little bit. Can be 10 minutes. I will ask everyone else that didn't enroll to leave the room. Okay, or you can go right now and prepare, copy everything that you need on the computer that you want to use. Okay, and at the exam time, 11 o'clock, the exam will pop up in the blackboard. You download it and you do it, and it's going to be done. And you have to submit it by 12:30. And read more information from the announcement. There's an announcement on the blackboard. I already announced about it. Okay. About the exam, if you remember. What is allowed, what is not allowed. We have 3 questions. Just 3 questions. It can be done just in half an hour. But we give you 1 hour and 20 minutes just in case.
30 minutes with your speed?
It can be done within half an hour, but we give you 1 hour and 20 minutes just in case. Okay?
How do we prepare for this exam?
Yeah, that's a good question.
How do you prepare for the exam?
It's really confusing.
Yes.
So please make it very